Be my guest.
All right, so let's start off with writing the correct Euclidean algorithm. All right. So 43. Is this big enough? I don't know if that's
Yeah. No, that's a bigger. Yeah.
I'm nervous.
Okay, I get you.
Wait, can Zoom see this?
Yes. If you're like in bounds, these are the bounds. Anything else is out of bounds. Yeah.
Good check. 38. 7. 5. Plus 3. 5. 1 times 3. Plus 2. 3. Plus 1 times 2. Plus 1. 2. 1. Wait. Wait. Did I mess something up?
Oh, 2 is equal to 2, like parentheses 1. Plus 0.
Yeah, no, that's right. I promise you that's right. Okay, so a way, like, we can, so what I like to do when I see this, before I see, like, these are the remainders over here, right? So what he was talking about earlier, like, how can we get 5? I couldn't really follow, sorry.
That's okay.
So I just, like, have 5 equal
I'll do better.
43 minus 1 times 38. You don't need all of these, but I like to do this for every problem just in case I need them. So it's 3 is equal to 38 minus 7 times 5. 2 is equal to 5 minus 1, 3. Yeah. And then 1 is equal to 3 minus 1 times 2. And you don't need to do this, but what I like to do to make it easier to read when I is it called linear combinations? Like when you plug in stuff, like we're going to be plugging in stuff. I just like to do a 1 times these values just to make it easier to see, and you'll see later. Chat. All right. So the question says, you guys have this. I don't need to read it out. We're trying to find like a 3 is equal to S times 38 plus T, but that's not a T. T times 43. All right. So we have a 3 equals something up here, right? And this looks like an S. This you know what I mean. So we have 3 equal to 1 times 38 minus 7 times 5. And I don't know how to explain this part. I just kind of know it. I see a 5 here and I see a 5 here. And I see 5 is equal to this. So I can put this stuff in place of that 5, right?
It's the same principle as if you substituted for a variable in a traditional algebraic sense. We're just substituting for an actual number instead of a variable.
I'm just gonna move this over. Oh God.
The key part here is to try to do some template matching, right? Look at the quantities you need and just keep in mind that when you flatten everything at the end, you're gonna have to have factors that are multiplied by the things that you're trying to find the linear combination of. In this case, it was 38 and 43. So you want to use the ones that have 38s and 43s, probably.
Oh, that's bad.
It's,
kind of look at that. I can rewrite these steps in a minute. So all we did to get from 3 equals 1 times 38 minus 7 times 5, I just substituted that 5 for this 5. So I got this. And now what we do, we distribute the 7 to these coefficients. Can I call them that? Yeah. 3 equals 1 times 38 minus 7 times 43 plus, because negative times negative, that's positive, plus 738. Then you combine like terms. I see we got a 138 and a 738. That's 838 minus 7 times 43. Now, if we look at what the question's asking on integers s and t, such as 3, you know what I mean. Mm-hmm. So something times 38 and plus t times 43. So in this case, we see the 8 is next to the 38. That'd be s. And negative 7, 43. That means t is negative 7.
Yeah. Yes. Yeah. Yeah. Okay.
So while you're coming up, I will also note 8 and -7 aren't the only solutions to this problem. But they're probably the easiest ones from the information that we have.
Yeah. So can anyone give me another solution? No? Yeah, I'll show that later.
There is at least one other solution mentioned in the rubric.
I did it the long way up. I started from the bottom, it's starting for one, and we multiplied into.
Yeah, that works as well.
Were you gonna show the other way?
No, it's okay. I'll do it later. It's not another way. It's just a way of finding more solutions.
Yeah.
Once you have one solution, you have.
You have technically infinitely many solutions.
Yeah, I was finishing there.
But
One. All right, folks, I want to make a comment about the Chinese remainder theorem problem. So you probably noticed that Sebastian did it in a way where he again reused the pre-computation that he gives you. I know that some of the ones that I've seen did not do that at all. You instead calculated the inverses yourself. You're free to do that. If you don't understand why, you can use the pre-computation. After our friend here completes it, I'll give kind of some intuition as to why that works because the key doesn't really say that. But you can calculate the inverses yourself. The important part really is that you know the CRT formula. And if you write down the CRT formula, that's one point. If you find the things, you just need to find the y's and the CRT formula, which are the inverses. And it's kind of easy to make mistakes there. So try to use that pre-computation. But if you don't, because you don't know how, and you get the right answer, we don't care.
yeah, so the given information is really just going to make it faster. It's not going to give you any like new information that you couldn't derive for yourselves.
Mm-hmm. And another thing is that for a lot of these problems, if you have some extra time, you really should be checking your answers, right? Like if you calculate an inverse, can someone tell me how you check whether it is actually an inverse? Yeah.
Multiply the inverse by the first number
Mhm.
and see if you divide by the pod, see if they give remain on one.
Yeah, that's right. And you have a calculator, so this should be pretty easy to do. But what I suggest is that you check all your answers. All the answers are checkable. You check them. For example, the linear combination result, right? Once you find S and T, what do? You plug in the numbers in your calculator and you make sure that it actually works. So try to check as much as your work as possible, either before moving on or before turning in.
And many of the questions that were on the take home are checkable that way, but not all of them. So just check the ones that you can and know that you won't be able to use a calculator to double check every single question.
So why don't you put like letters like the Y?
Oh, sure, yeah.
That way
We just like label them as variables.
Sure, yeah.
And maybe say a little bit about what you're writing.
Yeah, sure. Yeah, no, definitely. I'll explain all I can. Then we have one more we can deal with. This is do that. Okay, honestly, this isn't that difficult of a problem if you know what you're looking for. The first thing that we can start off with is the coefficients. What does that mean? The coefficients are 4, 3, and 23 here. It doesn't matter what order you put them in, but we'll go from least to greatest. So first we'll start with 3.
So you just have to be consistent about your ordering. So if you pick mod 7 first, you got to stick with mod 7 first. But other than that, it doesn't matter.
So the next part that we can fill in here, the mod product, what does that mean? So in the case of 3, we're looking at this right here. X, so 3 and then mod 12. So what we need to do is we need to multiply the moduli that aren't within this one right here. So we need to multiply 7 and 25. 7 times 25 right here. Okay. And we can do that for the rest of these just to make that simple. Okay. Before we move on to the more difficult part, which is finding the inverse. Okay. So for 4, again, what's the modulus here? It's 7. But we don't care about that. We need to find the product of the ones that aren't 7. That's going to be 12 and 25. Last but not least, we have this one right here. Again, the modulus is 25, but we don't care about what's here. We care about the other moduli. So 7 times 12. From here, we need to find the inverse. So I'm actually probably going to go into that area. I need a little bit more room.
This is off the
Yeah, it's off limit.
Oh, okay.
Yeah.
Sure.
That's why the
Yeah, then I can probably just do it right here.
Yeah.
Perfect. Okay. So let's start off with 4 mod 7. What we can see from 4 mod 7 is that we know that if we have a product of 7, if we do modulus 7, that equals 0. What does that mean in practical terms? We have 43 times 7 right here. If we take the modulus of 43 times 7, this becomes 0. So we can cancel that out essentially. So what this will mean is when we apply it, now we can do this. 1 is equal to -1 right here, the rest right here. Everything from here on, none of this because it's 43 times 7. Modulus cancels that out. It's 0. We don't care about it. So -1 times 25 times 12. But these numbers look a little familiar, 25 and 12. And it's because we have the moduli right here, 12 and 25. What this means is that we can take the inverse by basically saying that this right here, -1, is the inverse. And since we don't want that in negative terms, what we need to do is we basically add whatever the modulus is we're working with. That's going to be 7. So we do -1 plus 7. That will give us 6. So we found our first inverse. And you can definitely explain more as to like why that works.
Yeah, I'll do that.
second row.
All second round.
Yeah. The consistency is important.
Yes.
It's like confusing sometimes.
Okay, so now we have 3 mod 12. From here, we can see that the second row is 73 times 12. Again, we can apply the same principle. A product of 12, if we do modulus 12 on that, this becomes 0. So what we can do is 1 is equal to -5 times 25 times 7. Okay, again, these numbers are familiar, 25 and 7. So now the inverse is -5, but again, we don't want negative terms. So what we're going to do is we're going to add, we're working with 4, so we're working with 3. So we're going to add the modulus right here. We're going to add 12. And this is equivalent to 7. So the inverse here is 7. All right, last but not least, we have 23 mod 25. So we have 25 here. Again, anything that's a product of 25, if we take modulus 25, this becomes 0. So now this becomes 1 is equal to -11 times 12 times 7. So from here, again, these numbers are familiar, 12 and 7, 7 and 12. And so what we can do is we can say that -11 is the inverse. And like before, We don't want a negative term. The modulus we're working with is 25. So we're going to add 25 on, and this will give us 14. So now we put 14 right here. This last column is the easy part. We've done the hard work already. We don't even need a calculator technically, but we could basically just multiply all of these together. So for this entire row, this is going to be 3 times 7 times 25 times 7. This row will be 4 times 12 times 25 times 6. This last row will be 23 times 7 times 12 times 14. And these are equivalent to, if we had a calculator, let's see, so you start with 3, be something like 3,675. Second one will be 7,200. The last one will be 27,048. Now what we need to do is we need to add this column, the values from here down to here.
Yeah, but you don't need to do that. I think that's good enough.
Yeah, definitely.
Yeah.
Well, one thing I will add is we're actually going to be taking a modulo again on these things. So while it's nice and helpful to get these positive, it doesn't actually have to be positive, because in the same way we can convert the negatives to positives here, if we have negatives at this step, when we take the mod later on, we can convert negatives to positives again. So you can kind of leave it in whatever form you'd like.
That makes sense. Yeah. Good stuff.
Yeah. I guess I want to like say something more about how to get the inverses. So if you look at the key, guys, and like what was your name?
Ralph.
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 Like he said, I couldn't hear. I'm sorry. Like if we take mod on both sides, right? Like let me take for this guy. If I grab and I take more on both sides, I get like, let's say something here. I don't specifically care what. 7 minus 1, 25, 12, and let's say mod 7 here. Like he said, like here I have something that's like times 7. So it doesn't really change anything, right? Like if I have like 2 mod 5 and I add multiples of 5, right? I still get 2 mod 5, right? It's still equivalent. So that is why in the key, we're setting this to 0 because we can. It doesn't change anything. And once we do that, the key part here is to identify that if we use the associative property and we group it up like this, look at, and you just read it off. Look at what this says. It says, this is the thing that I want to find the inverse of, right? 25 times 12. This is the thing I want to find the inverse of. And it says that if I grab 25 times 12 and I multiply it by -1, then that's congruent to 1. So that is why -1 is the inverse. Does that make sense? So this is always something that you should kind of try to think about, like, how can I use the associative property to kind of group things up in a way that I can read off the inverse? And this is how you read it off.
Can I say something real quick?
Yeah.
So, this is great. I like to think about it a little differently, so I can also present a slightly different kind of mindset about how to think about getting these inverses. If you would like, sometimes it helps to see multiple ways to do things. So if we take our first equation, times 7 minus 1 times 25 times 12, I can also do a little bit of algebra to just rearrange the order that this is written. And I can say 1 times 25 times 12 is equal to, here on this side, 43 times 7 minus 1. That tells me that 1 times 25 times 12 is 1 less than a multiple of 7. Or in other words, the remainder is -1. Right? So in terms of mods, that tells me 1 times 25 times 12 is equivalent to -1 mod 7. And then in order to get the 1 that I want, I can multiply this whole thing by -1. So I get -1 times 25 times 12 is equal to 117. So it gets you to the same spot, but it's another way to think about it. So if it helps you to have one way or the other, yes.
If you did that, equal to 6.
So -1 is in fact equal to 6.
Yeah.
But if we multiply this whole thing by
Oh, never
-1,
mind.
then it essentially moves the negative sign. Because multiplication like that still works with modulo.
I guess,
Yeah, I see some
What
hands.
do we mod the final answer by, I think?
The final answer, I believe, is the
If mod-
product of all
the
three.
product of all the mods. Yes. So I guess I have another question now. Once you finish this, does anyone know how to check it? Can you check it? Because I mean, this is like quite a bit of calculation, right? Yeah.
I mean, if, like, you have used the calculator.
Yes.
You could you could add all those up, modify 2100, you get an answer, and then you could just plug it in as X in all those equations and see if it works.
That's right. So once you do all this complicated stuff, guys, again, check your work. And for this one, it's very easy if you have a calculator. You just grab your X and you check and you make sure that it's equivalent to 4 mod 7, and that is also equivalent to 3 mod 12, and also equivalent to 23 mod 25. So always remember to check it either at the end or when you're done. If you have time, of course. If you don't have time, then don't. So try to do it at the end at least. Okay, so the next one is combinatorics. Okay,
I can talk about this if you want.
I can do this. I'm pretty confident with this one. So let's talk about combinatorics now. No, I know a lot of you have issues with this one. It is kind of a hard one.
Is this number 3?
Yes, number 3. So let's go number 3. Oh, VOC. Oh yeah, we should actually go for VOC. Right.
Yeah.
You want to do that one?
You can take it if you want, and then I can take the combinatorics.
I like the combinatoric.
That's part of why I wanted to do this. Like,
Yeah. I guess, does any brave soul want to do B, or I can do that one? That one's quick. Okay, I can leave this. Oh, that's all right. So,
can you just give me the numbers for the problem?
you can read that. Let's go.
Thanks.
All right, quiet guys. We're going over another one.
We want to talk about parts B and C as well. So for part B, it asks us to give an inverse of 25 mod 73. So again, we could do a bunch of calculations for this, but we have some information that's already given to us that will make this faster. So in particular, we want to pick, yeah, no worries.
Yeah.
In particular, we want to pick the equation that has both a 73 and a 25 in it. That's going to be the one that's most helpful to us. So that happens to be the second one, which tells us 1 is equal to 73 times 12 minus 5 times 25 times 7. So again, I like to do some algebraic rearranging for these. So we're trying to work mod 73. So I want to know what this is in terms of multiples of 73. Right? So I'm going to bring the 25 over and move the 1 around. So we'll end up with 5 times 25 times 7 is equal to 73 times 12 minus 1. So again, in terms of moduli, this tells us that I can find a multiple of 73, and that's going to be 1 off from a multiple of 25 here, right? So that tells me that 5 times 25 times 7 is going to be equivalent to -1 mod 73. And once again, I can take advantage of the fact that multiplication still works just fine. and multiply this whole thing by -1. So I get -5 times 7 times 25 is equivalent to 1 mod 73. So that tells me if I want to know what the inverse of 25 is, I can take this quantity, and that works as an inverse. So that says -35. Now, if I want this in terms of a positive number, I can convert that. I can add 73, as we were thinking about earlier, and that'll give me positive 38. Does that make sense? No? Which parts are confusing? Yes.
You give us -35. Would it be an acceptable answer on the exam?
I would think so.
Yeah, it's fine if you leave it as that.
Yeah.
Yeah.
Yes. Yeah.
Yeah, I did the wrong thing.
No.
So this conversion? Yeah. So modulo here essentially means that this is what the remainders are going to be. And so what this piece tells me is that if I take 5 times 25 times 7, and I divide it by 73 times 12, I'll have a remainder of -1. Now that's a slightly weird way of phrasing it. So I could also kind of refactor this slightly. I could say this is 73 times 11 plus 72. Right? On board with that? So then if I were to do it that way, I could have a 72 here. 72 mod 73 is equivalent to -1 because it's off by 1. So I can make the conversion then at that step, if that is easier to think about in terms of remainders, because we don't usually have negative remainders. Does that help? All right. Other questions? Yeah. So I get rid of the 12 because what I care about is being a multiple of 73, not which multiple of 73 it is. Because all I care about is the remainder, or in other words, how far away from a multiple of 73 am I? It could be any multiple of 73. Does that kind of make sense? Yeah. So the particulars of it being a 12 aren't really important. It could be any integer x, and I would still have the same property. Yeah. Does that help?
Yeah, guys, just remember that when you have like this whole thing about like modulo, right? Like, I guess, right here. Like if I have like 3 mod 6, right? This will be congruent to 3 plus 6 times anything mod 6. Because if I keep adding the 6, when I divide this whole thing by 6, the remainder will still be 3. Does that make sense? So that is kind of also why the idea of like just grabbing and saying, well, it's a multiple of 73. This is kind of how a key does it, where we can just say, well, if we put a 0 here, we're still going to have the right thing. So then we just read off this whole thing here. That's kind of the same idea. So these are just two ways of thinking about it. One of them needs some like algebraic manipulation beforehand. The other one just requires you to kind of match the definition of what it means to have like this modular arithmetic. And then there's
So any other questions on part B?
How'd you get from 25 to -35 again?
Yeah, so -35 to 38 here, this part.
Yeah.
Yeah, so the -35 to 38 is
guys, quiet, please. Guys, quiet.
so the conversion between -35 and 38 is because these are exactly 73 apart from each other. And something that I kind of think about with mods is that they keep looping around from 0 to 72, and then you start back again. And so that holds true going larger than 38 and also smaller than 0.
Yeah.
So you can think about kind of going from 0 and stepping back 35 places.
Yeah.
Or in other words, starting at 73 and stepping back 35 places.
Just if you have anything negative, mod anything else, the way that you can always turn this positive is just by adding copies of the thing that in your mod B, right? Like in my case here, if I had this example, right? Like if I have like negative, I don't know, negative 30 mod 6, then I just keep adding 6 up until I get to the thing. In that case, I guess it would be 0. But I just keep adding 6 until I get a positive thing. And that's something you can do, because if you add the thing in your modulo here, then you're always going to kind of maintain that congruency. Even if the number's different, even if the number's negative or positive, you can keep doing that. So that kind of ties back to what Danny was saying about looping.
All right, I saw a hand over here.
Is it safe to assume that you won't ask us to do the long way on the test, and we will go with that first?
Yes. It seems safe to say that you will be given some of the information similar to this that you can use as a shortcut if you know how to do it.
Oh, yeah.
All right. I saw a couple other hands. Are there still other questions? Yeah. Yeah. So, once again, we're looking for an inverse. So you can check that by actually performing the multiplication and dividing by 73 and seeing what your remainder comes out to if your calculator does remainders. Alternatively, you could continue subtracting 73 until you get something that's smaller than 73, and that will be equivalent to your remainder as well.
Or you could just do the multiplication, then subtract 1. Because if it's an inverse, then it will be 1 mod 73. So if you subtract 1, then it's 0 mod 73. Then you can divide by 73 and see if you get an integer.
Yeah.
That's good too.
That's a good
tip for calculator use on this one.
Yeah.
It's a good one.
All right. Other questions on this part? All right. Cool. Part C for this question as well. Yes. All right. Cool. So this one is less related to the rest of the problem.
You should write the Fermat-Little theorem. That's all.
Yeah. So this one is one that's going to require you to realize that you can use another theorem, or at least that's the fastest and easiest way to do it. And so the relevant piece for this is Fermat's little theorem. So that gives us a setup where I've got P, which is a prime, and another integer A, which is relatively prime to P. I believe the book writes this slightly differently. It says P is not a factor of A. That's an equivalent statement in these situations. And so what the theorem tells us is if I have these two values, then I can do something kind of nice. I can take A to the power of P minus 1, and that will always be equivalent to 1 mod P. So the theorem tells us all I need to know is about these properties of P and A, and then I can do this. This is really nice because I can take 1 to any exponent and it will stay 1. So if I take this and exponentiate it to any x, that's the same as exponentiating 1 to any x, which is still the same as keeping it at 1. Right? Everyone on board with how we can use this theorem? All right, cool. So now the question actually asks us to figure out 5 to the 8,642, I believe. Is that the right number? Mod 11. So what would our A be in this situation? 5. Yep. So A equals 5. And how about P?
11.
P equals 11. Do those satisfy these requirements? Yeah. So in fact, if you pick two prime numbers, they will always satisfy these requirements. So I suspect you'll see a pair of prime numbers on the test because those are really easy numbers to find that will always satisfy these. Just a little hint. So now we know what A and P are. So what does Fermat's little theorem tell us about 5 and 11? Yeah. So that tells us 5 to the 10th is equivalent to 1 mod 11. So now I want to find a way to split this up in terms of 5 to the 10th. So I notice here, this ends in a 2. If I want a multiple of 10, I'd like something that ends in a 0. So I'm going to use the power of exponents, and I'm going to write this slightly differently. I'm going to say 5 squared times 5 to 8,640. Right? It's the same as this. I've just written it slightly differently. But now my exponent ends in a 0. Right? So now I've got a multiple of 10, which is really nice because that's eventually just going to become a 1. Right? So I can rewrite this again. 5 squared times 5 to the 10th to the 864. And now I want to put back in the mod 11, right? Because I know that's what I'm going to want. So the 5 squared doesn't change. But now I'm multiplying it by, what is 5 to the 10th mod 11? Yeah, just 1 to the 864. Right? 1 to the 864th power? That's still just 1, right? So I end up at 5 squared. And 5 squared, that's bigger than 11. I want to get something that's in between 0 and 11, ideally. So 25 is equivalent to what mod 11? Anybody? 3. Yeah. So it's 3. You could think about that being 3 plus 11 times 2. Right? So the answer for this problem is 3. Questions about that? I would recommend including the statement of Fermat-Soil theorem on your cheat sheet for the midterm, because that's a useful thing to be able to reference. In fact, I would recommend including statements of quite a few theorems on your cheat sheet because if they're in the textbook, they're things you can use. And so if you have the statement of the theorem, you will know when they're applicable. That's part of the statement of the theorem, is it always tells you under what situations can I use this theorem. And so if you have access to the statements of those theorems, then if you come across a situation wherein you can use it, you will have the information that you need in order to be able to use it. All right, any questions about part C? All right, cool. So I think Mario's going to talk some about combinatorics. Yep. Oh, the marker. Let's see right here.
So let me check something quick. So, about combinatorics, everything Danny just said is actually probably especially important for the combinatorics portion. There's a ton of identities, some of which we played more with than others. Like, there's Pascal's identity, there's the Voldemort identity or whatever. We don't know which one is going to be on the test, but you might as well write them down. There's also the multinomial coefficient, which did appear in this, and we're going to talk about it in a minute. So the first problem says, for problem 3A, it says that in a wedding where 100 friends are invited, 6 of those friends must be selected as bridesmaids, and one of those 6 is going to be the maid of honor.
So really quickly, just piggybacking on something Mario just said, there's a whole ton of identities in combinatorics. A lot of them can be kind of derived very quickly by thinking about how the particular problem is attained. So you could use multinomial coefficients for one of these. You could also just kind of think through the problem in a particular way, and you'll arrive at the exact same representation of the answer. So even if you're not sure where the particular identities are applicable, you can still kind of mix and match and combine them in order to come up with the same representation of the answer that some of these kind of pre-given formulas would give you as well.
That's right. In fact, I'll give an example for that in 3A, which I think is kind of cool because it ties into your homework. So we have 100 friends. These are quantities. This is, I guess, the one quantity that's going to be in every problem or most problems. Now 6 of these will be the bridesmaids. And from these, we're going to select one person who's going to be the what?
Maid of honor.
Maid of honor, yeah. Okay, so something I emphasized in the sections is that try to think about things in terms of product rule and sum rule. Because it turns out that if you have a combinatoric identity, if you have a combinatoric expression that has sums and products of either numbers or binomial terms, binomial coefficients, then actually that is kind of telling you what is going on. And just like we can create the identity by thinking about the situation, you can kind of reverse that process and try to understand what's going on. That's actually what the homeworks we're trying to do. In this case, we're kind of gonna, in the exam, we're gonna make you build the terms, right? So we know that we have 100 friends and we need to choose 6 of them to be bridesmaids. Now this is pretty easy, right? In how many ways can I do that? Right, 100 choose 6. And then, and the way I like to think about these, especially when I have products or processes that are sequential, is I kind of like to think about like I have a set of things and then I'm reducing that. Now I have 6 people in there. And from those 6 people, I'm going to select one that's going to be the maid of honor. So that kind of tells you very easily that in the next step, I'm no longer concerned with the entirety of the set, right? I'm just concerned about the people that I chose to be bridesmaid. So then that tells you that the number at the top, which is the size of the set that I'm choosing from in the next step in this sequence, will be 6. Because out of 100 friends, I will choose 6 bridesmaids. And then product rule, out of those 6 bridesmaids, I will choose, well, 1. Now, you can leave this as 6, but what I do recommend is that you don't, because I think that when you leave things in terms of binomial terms, it's actually kind of easier to reason about. It turns out that there's many ways of doing this. There's another way of doing this that I think is kind of interesting and ties back to your homework. Has anyone found a different way of doing this? Yeah.
You select one person out of the 100 to be the maid of honor first, and then you select the other 5 bridesmaids.
That's right. Because if you think about like the input output, imagine this like it's like an algorithm, right? The input is the 100 guests, and the output is going to be a set of 6 people, one of which is a maid of honor. So in practice, it doesn't matter whether I select the 6 people first, and then from that set, I select the maid of honor. I can select the maid of honor first, and then kind of build a group of people around the maid of honor. Does that make sense? And this is actually what you did in the homework. I can't remember which one, but if we were to do that, then we would have.
The homework problem actually generalized this situation in terms of n's and k's, not necessarily 100, 6, and 5.
Yes, that's right. So in 100, if I have out of 100 people, I choose 1 maid of honor. Okay, great. Now, how many people are left in order to build the rest of my set, right? Well, I can't like I can't like pick the maid of honor again. So we take her out of the population, and then we say, okay, out of the 99 people that are left, I'm gonna have how many people to choose for the bridesmaids? 5. And like Danny just said, yeah, in the homework you saw this very same thing. It was just kind of generalized. It was like n minus 1, k minus 1, and here instead of having this n choose 1, it just had n. So if we do the reverse thing, okay, imagine we do the reverse thing in the test. Imagine we do the reverse thing, and we give you something like this, and we ask you to make a combinatoric argument. My suggestion is, when you see just like a random n floating around, that tells you something. It's not in the same form as like a binomial coefficient, but it tells you something. Namely, you can imagine that this is actually equivalent to just n choose 1. because if you just see the n, that's kind of making you think, oh well, that is like the number of ways I can select one person out of a set with n people, right? So it's kind of important to try to get at least slightly comfortable deciphering the interpretation of what these identities mean. Okay, so, yeah.
Something else I will say when you're trying to come up with these is this one is particularly well suited to happening sequentially. And so I like to put together the pieces sequentially in the same ways that Mario just did. First, I want to pick the bridesmaids, and then once I've got the bridesmaids, I want to pick the maid of honor, right? And the problem is actually laid out sequentially like that. And so I would recommend that if you've got a problem statement that's laid out in that kind of sequential way, that you think about kind of building it up sequentially in the same way.
Yeah, 100%. Okay, now let's look at number B. So number B says there are 8 tables of 11 people and 1 of 12 people. In how many ways we can tell 100 guests which tables each should go to? So we have 8 tables. Let's just suppose that these are my 8 tables of like 11 people, right? And then I have my tables of 12 people, one table of 12 people. So I have my 100 people, and I have to grab and I have to assign them to these tables. Now, this one probably was tricky for you on the first time around because it actually involves the identification of this situation and matching it with a corresponding identity, which I believe it's called the multinomial coefficient.
There's a question in the Zoom asking if there's a way to turn off auto brightness because they think like your black shirt's messing it up and making a whiteboard harder to see.
That plugin video settings.
I guess it would be adjust for low light, maybe?
Yeah, so there's a setting that's automatically adjustable brightness, and you just need to toggle that on. I don't remember exactly what it's called, but it's at the top.
I think it is. I think I turned it off. Let me see. Let's do a test. No,
Still,
it might be.
it's like it's still on.
Yeah. Mirror my video. Touch. How many computer science students does it take to figure out Zoom?
I don't know if the lighting in the room.
I think it might just be at the camera level of my computer because I don't see.
Yeah, like it could be at your computer's camera level as opposed to the Zoom level.
Yeah. I don't think I see a setting, guys. I'm sorry.
Like you turned the appropriate setting off.
Mm-hmm. Yeah, I turned the only setting that mentioned brightness and adjustment in the same sentence. So I think that's kind of the best I can do. I'm sorry, guys. Okay, so back to this multinomial coefficient garbage. So if we have n objects and I want to distribute them across like buckets where each of them has a specified capacity, let's say M0, M1, M2, blah, 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 up to, let's say, MK. These are like the capacities of each bucket or group or set or whatever, however you want to think about it. Then we have this expression, M0, M1, all the way to MK. This is how you write the notation. And this is actually just equal to n factorial times M0 factorial, M1 factorial. As you can see, this will be kind of a big number usually. And then MK factorial. So in this case, it's just a matter of like recognizing that I have a similar situation, right? Like the buckets are going to be what? Anyone? Yeah.
You have 8 buckets that have capacity of 11 and 1 bucket capacity of 12.
Okay, you're giving me the capacity. The buckets are going to be the tables, right?
Oh.
Yeah. So the buckets are going to be the tables where I'm going to like sit my guests. And like you said, yeah, we're going to have a bunch of buckets are going to have 11, and then we're going to have, let's say, the last one's going to be the one that has 12. Now, something that's kind of interesting in this case is that if you actually do 11 times 8 and then plus 12 times 1, you get exactly 100 people. So there are no like, let's say, ugly things that can unexpectedly ruin your problem. In the next one, I think, depending on how you think about it, you need to be a little bit careful.
Can I
But-
talk about
yeah.
a different approach to get you the same answer
Yes.
for the tables problem?
Yes, although let me finish this part.
Yeah.
So once we have that, once we understand that, right, then it's just a matter of like grabbing that formula and plugging in the numbers. We have 100 people that we need to distribute, and then we will have all of our buckets here. Most of them are going to have the same size because it's going to be 11 factorial times 11 factorial, and then instead of writing them out like this, I can just like kind of wrap them all up with this nice exponentiation times 12 factorial. And that is where this came from. Like, if you read the key and you're like, oh no, where'd that come from? That's actually in the book. I think it's section either 6.4 or 6.5. And there's a bunch of useful identities there. So what I do recommend is that what I recommend you guys to study is write down the identities in the sheet. And then after you do that, read the example that's like usually immediately after, just to get like an idea of how you would go about using that.
And it can also be useful to, in addition to just writing the identity, write down like a brief situation where that came from. So for example, if you had this kind of generalized, then write down that like the M's are the bucket sizes and N is your total number of people or something along those lines to jog your memory about like what the variables mean. Because if you just had this formula, it would be a lot harder to figure out where to use it than if you knew like a little bit more about where that formula came from.
You wanted to show another way through this?
Yeah. So another way that you can think about this problem is kind of ties a little bit into the next problem as well. But I can think about ignoring the tables for a moment and just putting people into seats. And then trying to kind of compensate for the fact that I've put a bunch of people at tables in different orders, right? So this kind of sort of starts to give away a bit of the answer to the next problem. But if I just put everyone into different seats, that would just be a permutation of all the people, yeah? So how many ways would there be to do that? Yeah, so I'd have 100 factorial, right? And now let's say I wanted to say the first 11 seats of this sequence of 100 seats, those first 11 seats correspond to the seats at table number 1, right? So I want, if there's 11 people in those first 11 spots, I actually want all of the ways for a singular group of 11 people to be in those 11 spots to be considered the same, because I care about which people are at table 1, not which particular seats they're in, right? So the orderings of those 11 people would be 11 factorial, right? It's another permutation. So I want to divide out the ways that I've overcounted for table 1. And then I could say table 2 is going to be seats 12 through 23, right? And I have, again, a group of 11 people that I've permuted more than I need to, right? So I want to uncompensate for those as well. And eventually, I've got all 8 of those tables that I'm trying to like compensate for overcounting, right? And so then for the last table that's got 12 people, it's just 12 people first, I want to have my last 12 people, which is going to correspond to my last table. I want to not impose an ordering on them. And so you end up with exactly the same thing, but you don't actually need to have had the formula necessarily to come up with a way of thinking about counting this that ends you up in the same place. Yes.
Could you also do this one like in a sequential way that you hold this book?
Yes.
Like 100 choose 12 times 88 choose 11.
Yes.
So on.
Yes, you can think about it like that. It becomes a much longer and more unruly statement. So I kind of like this because it's a bit cleaner, but you can absolutely do that as well for this problem. Yes.
We leave that in dot 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 notation.
So
You could also
yeah, I believe you could.
You could also use this symbol, which is
Yes,
like,
as a product symbol.
yeah, this is the product. You know how you can like sum things up by using the sigma? Well, you can use the big pi, I
Pi,
guess.
it's a
The
pi,
capital
yes.
pi. You can use capital pi to like do the same idea, but for like
A product.
multiplying things, right? So like typically we saw like
So sigma is S for sum, pi is P for product. So
exactly.
you can remember that.
Yeah.
Yeah. So the 11s and the 12s are just the sizes of the buckets, or in this case, the sizes of the tables. So if you want to think about it with the formula, it's just plugging in the sizes. If you think about it as kind of building it up this way, it corresponds to the orderings on each table.
So let's look at the next one. The next one, again, the next one is one of these where that has like two kind of obvious answer. Oh, I had it there. And this one says there are 8 tables, blah, blah, blah. There are 8 tables of 11 people and one of 12 people. So same setup, same tables. Now, I do want to say in the test, that might change, right? Like maybe in the test, I don't know if he would do this, but maybe in the test, it's just like, like 8 tables of 12 people or something. Like those numbers may change. So make sure you read each question carefully, right? Yeah.
The
Formatted
like the format of the text.
of the text. I don't know. What? Yeah.
Topic will be discrete.
Well,
Okay, so now, so that the tables are the same, the guests are the same, but now it says, in how many ways can we tell 100 guests which specific seat at those tables each should take? So this one, you have 2 ways of doing it. One of them is by grabbing the result from the previous one, which was 100, and then it was like, yeah, I'm gonna write it in this term, in this way. So we have it like this. So this is one term, and it's like, okay, remember, this told us how we can like distribute the people in our tables, right? So like, we're gonna put like 11, 12, blah, blah, blah. Now, what we can do is sequentially, and that's product rule, we can look at each of these tables and ask the question, okay, I put the people in this table. Now, how many ways do I have to organize those guys? Which really just means how many permutations of this do I have, right? If I have 11 people in this table, then how many ways can I arrange it? Where order matters, right? Because like order matters because like these seats are kind of indexed, right? So how many ways can I do that? 11 factorial, yeah. So I have 11 factorial for the first table and for the second table, and blah, blah, blah. So I'll do that 8 times, right? And then I'll have that, and then I'll do the same for the last one. Now, if you remember the form that this took, this was 100 factorial, 11 factorial, 8, 12 factorial. Oh, well, wait a minute. I can cancel these. And yeah, of course, because if you think about it, if I'm going to end up telling people where to sit, it doesn't matter if I first arrange them into the tables or if I specifically give them the seat, right? Like whether I like split them up at the tables and then like say, okay, you guys in this table, you're going to sit like this, and you guys are going to sit like this. And I'm counting all the ways in which I can do that. You might as well like just count the ways in which you can assign people to a specific seat.
Yeah. So when I mentioned the other way to break this down, I mentioned that we can think about seats 1 to 11 being table 1, right? So if all you have is the information about which seat people are in, that tells you what you need to know about which table they're in. So you can think about it in terms of just the seat location and ignore the table location because you can derive the table location. So that's another way to kind of think about why I don't need to actually break it down into tables necessarily.
Yeah. But if you do it this way, it's fine. And if you do it this way and you don't see the cancellation, that's fine too. Like as long, here's the criteria, right? As long as there's no extraneous work that is incorrect, right? If all the work leading up to your solution is correct, and I can punch in the solution in a calculator and it'll give me the same as the correct answer, and there's a plausible explanation there, you're going to get full points whether you simplified it totally or not. At least that's kind of the expectation.
It can sometimes help that process if you briefly explain your thought process there. So if you say, this is how I'm counting it and here's my numbers, then that tells us immediately what you were thinking of. If you just give us your numbers, we have to figure out your thought process. And sometimes we're not great at reading your minds. So if any help you can give us there helps us give you more points.
Yes, that's right.
Soft hand over here.
Soft hand.
just the ways we basically distribute like 200 tables and then 11 factorial are making 1 factorial, it's just like ways we can place and add that specific tables.
Yeah, so the way I was thinking about kind of deriving this was to take the 100 factorial by just putting people in seats and then kind of dividing out the ways that I've now put the same collection of people at the same table, but in a different order, right? So if I have 11 people at the first table, or in other words, if I have 11 people in my first 11 seats, then there's a bunch of different ways to have that same collection of 11 people in those first 11 seats, right? And if all I care about is which table they're at, then I don't want to count all of those different variations as separate. I want to count those all as the same because it's got the same collection of people at the table. And so that's why I'm dividing by the 11 factorial for table 1, because I've taken those first 11 seats and I've counted a bunch of different variations on it. And I want to just count the one variation.
Yeah, I'm sorry. I meant like for the solution that we just got to put that right there on the board.
Yeah.
No.
Yeah. So basically, we're just adding that ordering back in. Right. So I'm saying the multiplication and putting it in the numerator is basically saying now I want to order those first 11 seats and also the second 11 seats and the third 11 seats.
Yeah.
Right. And so that's why they cancel, because dividing is taking out the order and multiplying is putting it back in. Right. So does that help?
Yeah. I guess in the book, there's an example. I can't really tell you the page because I have the 7th edition, but in section 6.5, I think it's theorem 3. And so there's an example under that actually explains how to derive this formula, because I know like the formula can appear a little bit weird, but like the way it's derived is actually similar to what Danny said, and also similar to what someone over there said, which is like essentially you grab like Cn, and then we grab the n0, and then we multiply by like, okay, well, if I had 100 people, I took 11 people out because I distributed among the first table. And then I have, okay, well, now I take those guys out, the 11 people, and I choose another 11 people. And you do like this. And then if you expand those out, you can imagine each of these are going to be ratio of factorials everywhere. And then some things are going to cancel out and you end up with that expression that I showed.
Yeah. Basically, the n0 here and the n0 here are going to start to have some parts that cancel. And then there's going to be an n1 here and also an n1 in the next term that's going to start to cancel. And so there's some cancellations there. And that's what ends up allowing you to kind of shorten it a bit.
Yeah, I realize that. I guess you can like do it like this. If you wanted to simplify it.
Would write it like that.
Although nobody
nobody
would want to, but you
I
could.
don't think anyone would really want to write it like that.
But this is kind of an example of how you would use this product thing. If you had a bunch of stuff multiplying and you don't want to do the ... you could like use this. It's kind of like an iterator. But don't do this.
If you have like 8 11s and a 12, you can do the 12 separately, and
Yeah.
it's a little easier. But
Okay, let's talk about the bus one, because during my sections, I noticed that pretty much everyone got this wrong, and it's easy to see what the problem is here, right? So in this one says, okay, we have the 100 guests, and we will have 2 buses, and we're gonna kind of have to ship these people to the venue or whatever, and we're gonna have 2 buses, and each of them is gonna have a capacity of 60. So because I have 100 guests, I will not really be able to like put them all in one bus. So the best I can do is to put 60 here and 40 here, right? That's the best I can do. If I have 100, I need the number of people in one bus and the number of people in the other bus to add up to 100. So most of you did, well, I have 100 people and I'm just going to put 60 people on this bus. And that's going to give me the number of ways because I'm going to fill this bus. And then I'm going to have some people left over, and I don't need to worry about those because it's always going to be the complement of like what I didn't put in that bus. And I'm done. But what's the problem there? Can anyone tell me what the mistake is? Yeah.
What if you have 50-50 split or 59-41?
Yeah, there's nothing in the problem that says that I have to make use of this entire bus. In fact, probably like if you're going to if I go to the bus and it's like there's 59 people and there's another bus that has like, I'm gonna go to the.
I'd want to go to the
bus.
emptier bus.
Exactly, right?
More space.
Exactly. So what happens really is that you need to take into account a bunch of different splits. Now, definitely one of the buses, I guess one way to think about it is like, okay, I have my extreme case, right? Where I have 60 people and I'm going to try to be roughly proportionate. And I have 40 people, right? But again, it doesn't have to be that way. I can have like maybe 59 people and I can have 41 people. And I can kind of like keep decreasing like that, you see? Because these are all possible kind of configurations. Now, if I'm telling you that each of these is a different way of doing it, right? It's not that I'm choosing, like, it's not a sequence of steps. It's like they're different parallel steps. What should that tell you that you need to use? Do you need to use a sum or do you need to use a product? Sum. So again, you should always try to think about that. Like all of these things, really, every time you see a sum or a product, implicitly that is telling you something about the structure of the problem. So anyway, so I can keep going down this right, and eventually you're probably going to have 50-50, right? But what is my floor? What is my floor? 40, right? Because eventually I'm going to hit capacity on this one. So then what I need to do is find a way to count all of these different guys. So before in the solution, the naive solution, the first approximation that most people did, you wrote only this. And as you can see, we're like vastly undercounting, right? Like vastly undercounting. So how do we do this? Well, we recognize that if these are all different ways of doing that, then that is like the domain of our beloved sum rule. And now I need to find a way. Now, the thing about working with sums and product iterators, especially like early on in a degree, it's like it may be kind of hard to like get used to the notation and see what goes where. So let's just say that this is K. K is going to go from what to what? What? 40 to 60. Okay, yeah, you can actually have some relative freedom in doing this.
So you can like compensate in different ways.
Mm-hmm.
So you could do 4 to 10 and multiply, or 4 to 6 and multiply it by 10 a bunch of times. You could do different things. You'd need decimals for that, but you could do it. You could do a bunch of different things. You could go 40 to 60 and subtract that from 100, and you'd be going 60 to 40 essentially. There's different kinds of ways you can put it together. You just essentially need to end up at the same set of terms that are getting added together.
Yeah. So does anyone have any questions about this? Yeah.
Can you real quick go over again why it's like when you know it's a sum versus a product?
Oh, yes. So these are all like mutually exclusive scenarios in the sense that if I have a universe in which there's 60 people in bus 1 and 40 people in bus 2, that will, even if similar people, if like 59 of the people here are actually here, that's a different universe than the one where I have 59 people and 41 people here. They're different situations. So that's why we count them different. They're different ways of doing the same thing.
So another thing that sometimes can be a helpful rule of thumb, these separate situations aren't building on each other, right? So I can kind of count them differently versus I can have situations where they're building on each other and I want to multiply those together. So for example, when we were talking about the tables and I was trying to add that order back in, I wanted to multiply all of those together because the orders were building on themselves, right? The ordering on table 1 and the ordering on table 2 have to work together, right? If I change the ordering of either, that's going to give me a new situation, right? So I need to multiply those together to think about all of the like built up possibilities. But here, the ordering on this bus doesn't impact all the ordering on this bus, right? So they're completely separate situations that I need to add together. to kind of put them together. Yeah.
I want to add that the way that I think about it is, so say you have a bus of 60 and then a bus of 40. In the other case, it's an or, so you either have 16, 40 or 59 and 41 or 58 and 42. And when you have ors, that's a sum of combinations. Versus when you have ands, like with the tables, like 11 people at this table and 11 people at this table, that's a product.
Yeah, that's a good way to think about it. Yeah. In fact, you can apply that to 3A, right? And say, well, I want 6 bridesmaids and 1 maid of honor, right? It's not like I want 6 bridesmaids or 1 maid of honor. In that case, you would use sum rule. That's a good way to think about it. Okay. Any last questions about this one? Because I know this was one of the harder ones.
Yeah.
Like, how do we count total busing answers? Like, if it's 100 choose 40, like I could be going on the rest, whoever's left.
Yeah. So that's how I think about it. At least I can accomplish figuring out which people are on which bus by knowing which people are on the first bus, and the remaining people have to be on the second bus. So at each kind of sort of distribution, be it 60-40 or 50-50 or whatever the distribution of people to buses is, then I can just pick that many people to be on bus number 1, and the rest have to go on bus number 2.
And it's not.
Yeah, so you can so Mario mentioned that sometimes it can be nice to include things in terms of binomial forms. So if I'm thinking about taking 100 people and picking 60 of them to be on bus 1, afterwards I'm taking 40 people and picking 40 of them to be on bus 2.
Yep.
And so this is equal to 1, so we normally omit it. But it can be helpful to include sometimes so you can see where those remaining 40 people are going.
Yeah. Yeah, and another way to think about this, so we're trying to give you all the ways to think about this. Another way to think about this problem is actually thinking of the buses and the guests as like binary strings. So you can say, okay, well, the slots in my binary strings are going to be people, and that's going to be like 100 slots, right? And then I will put a 0 for them going into bus 1 or a 1 to put for them to go into bus 2, right? So like this could be like a way of doing that. And if you remember from our discussion section and probably from some of the discussions with Danny and Chelsea, it turns out that when we have a situation like this, if I choose where to place the 1, that fully determines the string because the rest is going to be 0. And it's the same idea, right? If I choose where the people are going to be in bus 1s, then since there's 2 buses, and this is why we can make this analogy with binary strings, since there's 2 buses, then the other people are going to be in bus 2, just like in the situation here where the position of the zeros is fully determined by where I choose to put the 1s.
Yeah. So you could also kind of increase this to an arbitrary number of buses. If I had 3 buses, I could do this in base 3. It makes it a little more complicated here because I have to pick the people in bus number 1 and the people in bus number 2, and then bus number 3 becomes 4th, right? Et cetera, et cetera.
Yeah. And this is actually ties nicely into our next question. Yeah.
Could you have done this with like the linear equation model? Say like x1 plus x2, is that true? Or would that not work?
So x1
you have to incorporate the limits of 60.
Yeah, with like x1 and x2 are less than or equals.
Yeah. So you could probably do it like that, but at least if it were me, I'd essentially boil that down to doing another sum, but counting it with stars and bars there. So I think it would boil down to the same thing.
The calculation will be the same. It's just like
another way to think about it.
Yeah.
So it should work.
It should work. And the best way to see if something is works is not just to email the TA, to message the TAs, email the TAs, ask the TAs, but try it yourself. And then like plug in some numbers and go on Wolfram and check it out, right?
If you think it should work but can't get it to work, that's a great time to come talk to us. Because y'all have really great instincts. So if you think a method of doing something should work, chances are there's probably a way to make it work.
Yeah. Okay, so now let's go to this last one. And we also got tons of questions about this one. So this one says, the party venue promised to send an itemized quote of no more than 15K with the 4 items: personnel, venue, drinks, and food split into separate parts. In how many ways can they do so if all the items are multiples of $100? So I want to point something out here. The setup of the problem says 15K, and then it says that all the items are multiples of $100. And there's a nice little hint, basically, or next little step, that Sebastian tells you how to set up that equation. He tells you how to set it up. And then you notice that, oh, why is the 150 there? Because it's 15K divided by 100. Okay. Do not necessarily expect that that's going to be in the test, right? Like, what happens if it's like 20K and then, like 10, multiples of 10, right? It's not going to be 200 anymore, right? It's going to be 2000. So then you want to make sure that if the hint is not included, you understand the setup of the problem. Because, I personally, like, the first time I read this, I just, like, my eyes zoomed it straight to the equation, right? And I didn't even notice the 15K 100 part. It was not until I read it after that I noticed, oh, that's why it's 150 and not 15K. So make sure to pay attention to that. Just read the problems carefully, okay? Okay, so this one is very interesting because if you look at the key, there's an X5. There's an X5. We have 4 different classes of items, right? And yet we have 5 variables. Can anyone tell me why? Yes.
So right now it's set up in an inequality form. Well, like, can't really do this unless you have an equality. So basically what you actually have is like, you just like make it so it's 150 minus some X5 and you bring it over.
That's exactly right. So
when I was explaining it, I was kind of thinking about it as like a leftover amount, right? You cap out at 150 or 1500, however you want to think about it. But if you didn't get there, there's some kind of leftover amount, and that's what I think of as X5 representing.
Yeah. So there's 2 ways of like thinking about how to arrive at that and constructing that dummy variable. One of them is the way our friend over here said, which is like, well, if I need to be less than or equal to 150, that is the same as saying that I have to be equal to 150 minus something. I'm going to use a different name for this one. It doesn't matter if I don't call it X. Mathematics doesn't care about that. So let's call it C5. Now, if I have this, and I say that C5 needs to be an integer, then necessarily, if you think about it, okay, in the best case, this is 0. I guess in the worst case for the people of the party, this is 0, and this is going to be 150, right? And in the best case, this is 150, and they don't pay anything. And then what we can do is like that manipulation where we put it to the other side, and then we get plus C5 equals 150. Now, the other way to think about this is to like not do the thing on the right and then move it to the left, but to just straight up think, well, I have these guys, they need to add up to less than 150. So I'm going to have this dummy variable that's essentially like catch all the difference from 150. This is going to say like, okay, if this is non-zero, then if this is non-zero, like let's say that this is 5, then you know for a fact that all of these guys, if this thing plus 5 equals 150, then all of these guys need to be 145, which is less than 150. So that's kind of what motivates this setup. And once we do this, it's easy. You've done this in the homework like a gazillion billion times, right? You just say and you identify what your n is. In this case, the n is going to be 150, right? And you identify your r or whatever letter you want to use. It's going to be 5, and then you do like, what was it?
N plus r minus 1.
Plus 5 minus 1, and
choose either n.
Yeah. Yeah. And then you just
it would be 4.
Oh, sorry. Yeah. Okay. All right. Let's just do it. It's actually better computationally if you for some reason want to do this. So yeah, that's how we arrive at it. And hopefully this is easy to see why it is this way now instead of having 4. Why we turn into that way. Now there's another way of doing this that is, you could say it's less elegant, but it's just as good. Yeah.
Where you got from?
Oh yeah, because we have five variables. Yes. Yeah, so, but but actually I want to take a step back to the theory of this problem. Why is it that it is 5, right? Like I know that when we did the homework, a lot of people would just think that n is 5 and that r is 150. Yeah.
Stars and bars.
Stars and bars. Yeah, you can think of these. The way I like to think about this is to think about each of these variables as a box, right? And R counts the number of boxes that you're putting or that you're either taking from or putting in. And I like to think of these as like the boxes. And then the way then what I think is like, well, I have to like distribute the n over these boxes. And what that means would be like, okay, I'm gonna like, you can think about like putting in or sampling from this box. And I'm gonna say like, okay, I'm gonna put like 3 here, and I'm gonna put a bunch here and a bunch here. And that is kind of like analogous to that star and bars example that someone mentioned.
Yeah. So you can think about stars and bars in several different ways. You can think about distributing the stars among the x's. You can think about the stars coming together from the x's. There's different kind of analogies you can think about it with.
Yeah. There's another way of doing this that I don't know how many of you did it, but it's actually, it completely bypasses this dummy variable construction. You can actually solve it directly. But if you solve it directly, you need to look at different situations if you think about it. Because if I write my equation again, I don't know why I deleted everything. It always happens. If I have this, right, then think about this. This implicitly sets up several situations. How many is it going to set up? 151, right? It's going to be 151 different situations. It's going to be the situation where, I'm just going to do like this, where the sum of the xi equals 0. And also a situation where the sum of the xi equals 1. And also a situation where the sum of the xi equals 2. And so on and so forth. Does everyone see that? So then I can just like look at those situations and construct a sum. And sum all of those situations because they're going to be mutually exclusive, right? Like the solutions of the xi that make the equation equal 0 is going to be different than the solutions of the xi that make it equal to 1, right?
If you think about it, like if the equation is equal to 0, it can't also be equal to 1.
Yeah.
So I have to count those separately.
Yeah. So then I do the same kind of idea where I have my minus 5, minus 1, and then choose. But now what goes here?
Plus the quantity 5 minus.
Now what goes here and here? And here. Right? Like now if I make this like my k, and I say, okay, go up to 150, start at 0. Now I'm going to be counting all of those cases. Now, it seems like a little bit weird. I have like a sum of 150 things. Is it really going to add up? And yeah, it turns out that they do. Like you can put it on Wolfram or you calculate. Well, probably not. Maybe a calculator.
Depends on what kind of calculator.
Yeah, it depends on your calculator. Usually, one fun fact about all of this combinatoric stuff, combinatorics kind of blow up computers. Like typically, it's really hard, and actually discrete optimization and processes where you have to look at all the combinations and all the stuff. Like even these kind of things where you have to like explore, like, you know, when we gave you the problems where you have like the equation set equal to something, but then you have some constraints on this, that would be kind of like linear programming, and it's actually not so simple.
So like with this, with the formula we have for stars and bars, it looks like a pretty easy solution. It's actually a really, really, really big number. So that's part of why it blows up computers, because it looks kind of simple, but the calculations get really, really huge. Because factorials grow really, really fast.
Yeah. Like I think that for this, it was either on the order of 5 million or like 50 million when I plugged it in. But that's with like 4 variables in a bound of 150. Now imagine if I have 100 variables
and a bound of 10,000.
Yeah, I mean, so yeah. Okay, so I think that's it for problem 3.
One last thing I'll mention on this is if you want your variable to show up in fewer places, then you can use the fact that I can also stick the 5 minus 1 down here. and now my variable only shows up once instead of twice. Sometimes that can help you with bookkeeping if you don't want to make sure that you're correctly compensating for your variable in multiple places. Sometimes there's equivalent solutions that use that variable less.
Okay. So I guess now we can move on to problem 4, and I think is that the it's 2 more. Wow. Okay. So what time is it right now? 7. Okay. Yeah, we're just gonna finish this test, and I can probably stay a little bit longer also to answer some questions.
Yeah, I'd love to have some time to field questions. So
Yeah.
I don't know, we could try going a little faster through the problems if people would rather have time for more questions, or we could spend more time on the problems if it didn't come with all that many questions. What would y'all prefer?
Supposed to be going through some stuff during lecture tomorrow.
Oh, is that so?
Yeah.
Okay. Okay. Okay, let's just keep going with this then. I do need to use the restroom, so I can go. Okay. Yeah. Oh, I think this one. Yeah. Oh, let me check the battery on this. Okay. I need to find a way to plug this in.
Yeah.
So is this helpful so far, guys? Anything we can do better? Okay. All right. Sorry about that mishap at the beginning. I got a little bit of stage fright.
Yeah.
Exercise, I just need not the specific exercise, but statute said something about that not being included on the test would take up too much time.
What was the topic on 5?
Yeah, I'm solving a linearly.
Yeah, that one. Yeah. So, I don't know if I heard that from Sebastian, but if he says that was not going to be there, it is a time-consuming problem. So, that seems reasonable. I know he said RSA in an announcement. He said RSA stuff was certainly not going to show up.
Oh, now yes.
But yeah, like time is an issue.
I don't want anyone to.
This, so that would make sense. Yes.
Does anyone know where the restroom is around here?
Right.
Yeah, so basically it's to be solved.
I don't know.
Specifically, homogeneous also experiences. What homogeneous just
I like some jokes. I had to talk about things. Talk about
Right, so I'm gonna present problem number 4. from the take home. So this talks about the setup here is we have we're sending a letter and there's we have stamps that are worth 3 cents and stamps that are worth 7 cents. And when you to put we want to count the number of ways we can order the stamps worth a total of n cents for any n. So this is the a sub n is like a sequence that we want to be able to compute, or we want to find a recurrence relation for this. So that's what part A asks. So when trying to derive a recurrence relation for any general n sense, we want to look back at like previous terms and figure out like which previous terms of the sequence would be useful in helping us figure out a sub n. So which we know we have 3 cent stamps and 7 cent stamps. So if we're just trying to do an n cent line of postage stamps, if we start with a 3 cent stamp. All right, okay. So yeah, we're trying to compute a sub n, and to derive the recurrence relation, we want to figure out which previous terms, which a sub anything less than n is useful to figure out a sub n. So if we want to sort of build our way up to putting n cents worth of stamps, if we only have 2 choices of what we can start with. We can start with a 3 cent stamp, and we can start with a 7 cent stamp. So if you start with a 3 cent stamp here, then you to fill in the rest of the stamps to sum to n cents, you need a sequence of n minus 3 cent stamps, n minus 3 cents worth of stamps. And the recurrence tells us that this is a sub n minus 3. So if you start with a 3 cent stamp, then you have a sub n minus 3 ways to fill in the rest of the stamps to get to n cents. And we can do the same thing if we start with a 7 cent stamp. And these are 2 separate ways of doing this task. So we use the sum rule.
So they're separate because if my first stamp is 3 cents, I can't also have my first stamp be 7 cents. So I want to count those separately and add those together.
Yeah, the problem specifies that the stamps are in an ordered sequence. We want to count the number of ordered sequences of stamps worth n cents. So if we start with 7 cents, alternatively, we need to fill in the rest of the sequence be worth n minus 7 cents, which there's going to be a sub n minus 7 ways to complete the sequence. There's that many unique sequences of n minus 7 cent stamps, which is that's what our a sub n recurrence. That's how it's defined. That's how we define it. So this is our recurrence relation in general to solve for a general n. But we need some initial conditions or base cases to kind of set us up from the beginning. And then once this n is big enough, let's say once we get up to 7, then we can compute these from the ones we've already figured out explicitly. So any base cases, a sub 0, we can say a sub 0 equals 1. There's like one way to have an empty roll of stamps. A sub 1, a sub 2 are both 0 because the minimum worth is 3 cents, so we can't make 1 or 2 cents total. A sub 3 is 1. We just put a 3 cent stamp. That's the only way to make 3 cents. A sub 4 and a sub 5 are going to be 0. There's you can't have a 7 cent stamp, and if we have a 3, then there's no way to complete to not go over 5. Similarly, a sub 6, we can't use a 7 cent stamp, but we can use 2 3 cent stamps. So we're going to have one way to do that, which is to make 6 cents, which is to put 2 3-cent stamps. And then yeah, a sub 7, we can explicitly confirm that this is 1, because you have to use a 7-cent stamp. You can't make 7 out of 3s. But we can also verify that we can just plug it in that this recurrence holds up, that a sub 7 is going to be equal to a sub 4 plus a sub 0. A sub 4 is 0, a sub 0 is 1. So this right-hand side also checks out just as a sanity check that once we start with 7 cents, there's one way to complete it, which is to do nothing. All right.
How do we know like how many base cases we need?
So that's a great question. It will depend on the problem. Do you want to know about like this particular problem?
I mean, I guess for this one's like 7, right?
One
Yeah.
thing you know the recurrence relation, then like you need to know sort of how far back you need to look back to be able to use it.
One thing that you can definitely do is if you build your recurrence relation first without necessarily thinking about your base cases, you need to make sure that you have enough base cases so that whenever you start actually using this formula and not the base cases, your indexing doesn't break, right? You don't get like a negative index
So
array, you know.
I can't start this at 5, for example. This won't start working at 5 because I'd be looking at a sub negative 2, right? And I can't look at that. So as far as like base cases for recurrences in particular, for this I'll need 7 base cases so that I'm always looking at something valid. Right? If you're talking about base cases in strong induction, when we're doing recurrences, you can use the same principle, right? My strong induction proof would need 7 base cases to handle this, although it doesn't actually start at 0. So it would be, I think it's 12 to 19 on this example for 7 base cases. In general, the recurrence here is kind of telling you, at least how I think about it, like how far back I have to reference. Right. So here, if I'm looking at n, I need to reference up to 7 prior in order to get this information. And so if I'm generally have an idea of how my strong induction proof is going to look, I'll have an idea of how far back I'm trying to reference. And that's going to guide how many base cases you need. So if I'm always looking back at least 5 spots, or I guess at most 5 spots, I'll need at least 5 base cases to kind of cover my ability to do that when I'm looking at really small portions of my inductive step. So right, my inductive step is going to start working right at the end of my largest base cases. And so I need to still be able to look back like into my base cases essentially at that point. So I kind of sometimes think of them as like a buffer to make sure I'm always looking at valid things. Does that help answer that? I see a hand. Yeah.
I don't understand how you set up the installation. A sub n minus 3 minus 7. Well, I recognize that the numbers right, 7 plus. Why is it n minus 3 plus minus 7?
Okay, do you wanna? Well, I can give an intuition about that if you want. And I'm gonna do a little rewriting of variables. Let's look at n plus 1, just I guess because I think it makes it kind of easier to see. If I grab all of this and I add plus 1, like nothing really changes if you think about it. But I think it's kind of nicer to reason. So this says that I have n, like if this says like assume that I have n postages and I wanna have like the ways of like getting the n plus 1. Now my options are adding 3 or adding another one of like 3 or 7, right? So if I have like n, let's suppose that this is n, and let's suppose that this is n, and I want to add like the n plus 1. This is similar to the case of like the binary strings that we saw, I think, in class at one point, where I'm going to look at the options. Well, if I'm adding like a 3, then I can just count the number of ways in which I have like okay, do I want to stop at n or do I want to stop at n plus 1? Let me look at n plus 1. if I'm adding something here, then I can just like know, well, I'm adding 3 of them. So I look at the number of ways in which I can do n minus 2. So n minus 1, n minus 1, n minus 2. And I'm like, well, if this is like a valid postage here, and this counts like the number of ways, if I add 3, then I'm gonna have, or I guess here, 1, 2, 3, and I'm gonna get to that n plus 1. I'm not sure if this works with everyone, but for me it works. So, and then if I'm instead not adding the 3, but I'm adding the 7, if I go back and I look 6 back and I add 7, I get n plus 1. Does that make sense? No? Okay. Someone else can try.
I know, like, I think this visual probably would have helped more than kind of going past through it, but the way I kind of think about recurrences is if I'm trying to figure out a sub n for a general n, then recurrence sort of you're referencing previous, so you're referencing like indexing something that's less than n to be able to figure out what a sub n is. So if you're referencing n minus 1, then you think about the problem structure, you're like, if I can make n minus 1 sense, does that help me get to n sense? And when you think about it like that, like the answer is not necessarily, because if you have a sequence of stamps to get n minus 1, you can't use that directly to make n because you don't have a 1 cent stamp. But if you have a sequence of n minus 3 cents worth, then you can use any of these. You can start with any there are this many sequences that you can sort of use to build up to n cents. And there's one way to complete it, which is to add a 3 cent stamp.
I tend to think about going in the opposite direction, if you don't mind. If I want to build up n stamps or n cents with stamps, then I can think about like building up my series of stamps, right? It can be either a 3 cent stamp or a 7 cent stamp. And so I can think about trying to get to n cents in 2 ways. The first stamp could either be a 3 cent stamp or the first stamp could be a 7 cent stamp, right? So let's say I first put a 3 cent stamp there. Then I can put whatever number of stamps there are after it. It doesn't actually matter what the number is. But I know that if I'm going to be able to successfully create that n cents with my first stamp being a 3 cent stamp, that the rest of this has to be n minus 3 cents, right? Because yeah, so my stamps have an ordering, right? I have to put my stamps on in an order for this problem at least. So I'm just saying one way to create these n cents might be to start by putting a 3 cent stamp on and then figure out what the rest are going to be from there, right? Yeah. And so the rest of those are going to have to be a series of stamps still, and it's going to have to sum to n minus 3 cents, right?
Can you break that down a little bit?
Yeah, so if my sequence of stamps sums to a total of n cents, then if my first stamp is 3 cents, the rest of my stamps have to sum to n minus 3, right? On board with that?
Yeah.
Yeah, exactly. And the rest of my stamps are still a sequence of stamps, right? So these stamps that sum to n minus 3 cents represent a way to put postage worth a total of n minus 3 cents onto a package, right? And so the number of ways to do that is going to be counted by a sub n minus 3, right? So in other words, the a sub n minus 3 counts this collection of stamps preceded by a 3.
7 is just if we start with a 7.
Exactly.
Okay, that makes sense.
Yeah.
One last way of thinking about it that maybe works better. So I guess again, let's suppose that like this blob, this amorphous blob is my n cents from the stamps, right? So because it's ordered, I can like focus on like the first, or I like to focus on the first one because we're building from the previous one. So like I'm like adding, wow, it looks like sort of sausage. So this is my like my amount of things, and I can like have this in different ways, right? Like imagine this is 3, 7, 3, 7. I have different partitions of this. I don't know what the partitions are if I'm counting like all of them, right? I don't care about specific partitions, right? But I can definitely tell you something. Like if I'm building from the previous partitions, right? And I have the option of adding 3 cents or 7 cents, that the last bit of cents of postage that I'm adding will be either like the 3 or like the 7, right? Let's suppose that this is longer than it appears. So these are like my options, right? So this is the situation in which the last thing that I add is like 3 cents. And then that means that I have the 3 cents, and then I have n minus 3 cents. And for each possible way of having n minus 3, I don't know what the partition is, right? Like it could be like this, or it could be like this is 7, 3, 3, 7. I don't know what it is. But for each of those, if I add a 3 at the end, I will have n stamps, right? For each of these, like n minus 3, and then I have the 3 at the end, right? So I don't know how many partitions, what the partitions are, the specific. I'm going to count all of them. How do I do that? an minus 3. Now, this is going to represent all the possible partitions I have of this rectangle that correspond to the sequences of 3s and 7s. And for each of those, for each specific partition that I can think of, because they add up to n minus 3, if I add the 3 at the end, then I'll have a new one that has n, right? So then I count, okay, the number of ways in which I can have my sequence of postage cents that they add up to n, because I have to add something at the end, and that can be 3, will be, for this situation, will be an minus 3. Because for each of the combinations that this an minus 3 counts, I can add 3 at the end and get a new one that has length n. Yeah. Yes, and in fact, this is another example of the sum rule.
Yeah.
Yes. And then we do the same for this one. I know that I'm going to have to add something at the end. Like if it's sequence, if it's nicely ordered, what are my options for like the last bit of cents? It can be 3 or it can be 7. So then I look at the situation in which out of my n stamps, the last bit that I add is 7. Okay, well, that means that everything before is n minus 7. And how many ways do I have to count that? A7 minus 7. And for each combination that A7 minus 7 counts, for each, I guess, permutation, I can add the 7 at the end. And now I get n cents. Did that work slightly better? Better than before, at least? Okay, that's another way of thinking about it.
Sorry, we kind of took over your
right.
problem.
Yeah.
Awesome.
Continue, please.
All right. I guess I could. That kind of covers A, but part A.
Yeah.
But I think there was just like one other thing that I think is slightly more efficient. I don't know like how, or if it's like not good practice, but if you define like a sub 0 to be equal to 1, and then a sub I is equal to 0 if I is less than 0. So you just like extend this to the negative numbers and say that if your index is negative as just a 0, then you can start from 1 here, and this like recurrence still holds. So it's like I don't know if that's like a
I would say it's not always good practice to do that. Sometimes you will get recurrences where there actually isn't a pattern to your initial conditions. There's only a pattern once your recurrence kicks in. So for example, I could say that this recurrence holds after n is equal to 7 and higher, or n is equal to 7 and higher, and I could give you random initial conditions for A0 through A6, and you'd end up with a different sequence. This recurrence relation for it would still hold when n is greater than 7 or greater than equal to 7. So just because it works for these values when you do it like that doesn't necessarily mean that that's always going to work out that way. So it happens to work here, but I wouldn't count on it. Does that make sense?
Yeah, and then it's like also not really a sequence. It's kind of like a function on the integers. There's like no beginning to it. So if you need a beginning, then like it's not useful. Yeah.
It's the kind of thing that like sometimes works, but you've got to be particular about when you're saying it works. So I would err away from it, but you could try to make it work.
Okay.
Yeah, like I guess it works nicely when whatever your recurrence relation is like a sequence of like the immediate previous thing or like the immediate thing 2 steps behind. But when you have like multiple things, right, then it becomes a little bit harder. Like if I give you like a linear sequence or a sequence that is like an alternating sequence, you can probably like squint at it and find the pattern, right? If I give you the Fibonacci sequence and you've never seen it before, you're gonna have to squint a little bit harder because that builds on previous 2 terms, right? And this is a similar situation. Now, if you have a recurrence sequence where you have a bunch of base cases and then the recurrence relation kicks in a way that's not like very like the pattern is not so obvious, then you're kind of out of luck. So I would suggest to always kind of try to think about like the sequence generically in terms of like, okay, if I have n, how can I build that in terms of n minus whatever?
So I guess the last thing I'll say about that word avoiding, if we think about the Fibonacci sequence, it's always the same because I always start at the same spot, right? My first 2 are always 2 ones, or you can include or uninclude zeros at the front if you want. But it always starts 1, 1, 2, 3, etc. If I told you I want to take the Fibonacci sequence, but I want you to start with 2, 2, you're going to create a different sequence. So it's got the exact same recurrence relation, but it's got different initial conditions, which gives you a different sequence. So the initial conditions do matter. You're not going to be able to like use the recurrence relation to figure out what your initial conditions are. Your initial conditions are actually going to inform the sequence. Does that make sense? So yeah, that's what I have.
You may continue.
Okay, so the next part is like the proved by strong induction that
an is always
greater
greater than 0 for n greater than 11.
That one actually suffered from
I think
the one where it's kind of hard to see.
Yeah, it was
I think I don't
not like
since part B, I'll keep the recurrence up because we're gonna use it
really counts. So it must be.
So basically what this is saying.
and then we want to prove
Put together. Exactly.
Yeah.
That's how I do that.
we'll prove that a sub n is
Like slight changes in the way cards.
Taking the number of generations in the ratio transiting to start because I can help the secrets using it's harder to calculate ratios directly. So we do that we convert our problems into
Yeah, that's what they want to try to decide. Actually, right.
so for part B, I'm gonna continue with problem 4. We're asked to prove that a sub n is greater than 0 if for any n greater than 11. So you can think of it as if you can also say n is greater or equal to 12. So our base case is going to be 12. We're going to show, if we have at least 12 cents of stamps, then there's always at least one way, or there's always at least one way to make 12 cents of stamps. So this is, an induction proof. We'll start with n equals 12. And we want to verify that a sub n is greater than 0. So the way, or equivalently greater than or equal to 1. So we want to find, if we can find at least one way to actually order the stamps, then that gives us a sub n greater than 0. And in the case that n equals 12, we can achieve this by ordering, doing 4 3-cent stamps. And that's one way to make 12. So we can sort of explicitly verify that a sub n is greater than 0. we have at least one way of making 12. And it asks us here to use strong induction, so we might not be done with all the base cases. So if we were to try to, prove that it extends to, and from like, if we know it's true for K, if we wanted to show it's true for K plus 1, if we start K plus 1 here, then we'd have to reference back to K plus 1 minus 3, which is K minus 2, which we don't have that. We can't prove it for 13 using an inductive step because we'd have to reference 10. So we want to continue and prove some more base cases explicitly. N equals 13. We can get that by using 2 3-cent stamps and a 7-cent stamp. So that's also a sub 13 is greater than 0. We check that explicitly. And similarly for n equals 14, then we can do it with 2 7-cent stamps. So a sub 14 is greater than or equal to 0. And we could, since we are referencing a sub n minus 7, you might think that we want to do an additional 7 base cases just so we're adding things so we can kind of figure out what this is. But we only want to prove that every a sub n is greater than 0. And if we know that like a sub n minus 3 is greater than 0, then we don't care about a sub n minus 7 because this already contributes a positive to the a sub n, and this can't be negative. It can't cancel out the positive in any way because we're counting like the number of ways to do something. So it's if there's no way to do it, if there's 0, otherwise it's more than 0. So we can always say this is greater than or equal to 0. So we can stop with the base cases here and we're now do an induction step. So we'd assume that like for some K, that a sub K is greater than 0. For some K that's like greater than or equal to 14.
Well, it's strong induction, so you have to set up.
Oh yeah. We'll assume that for some K is greater than or equal to 14, we can use the fact that everything from 12 up to K, we've already shown sort of how that there's at least one way to do it. So for some K greater than or equal to 14, that for all I from 12 up to K, a sub I is greater than 0. So essentially for any number from 12 up to K, we've already we can assume all of these because we'll need to show that it's true for 15. We're going to need to use that it's true for 12. We can't use the immediate predecessor of 14. Yeah.
Just briefly mentioning what I mentioned before, the idea of kind of having a buffer with your base cases. So here, our Ks are going to want to start at 15 is basically the smallest that our inductive hypothesis is going to consider. And so we're going to need to reference back 3 spots, which is going to get us to N12, which is our earliest base case. So like this is kind of like the smallest amount we can get away with because we need any smaller and our buffer wouldn't be enough to get us to something that worked, right? If referencing back 3 got us to n equals 11, you can't actually make 11 cents with 3 and a 7. So we need to have at least enough of a buffer. I'll also note that you can never go wrong with too many base cases. So if you aren't sure, err on the side of putting more down. Mm-hmm. I always do that myself. I usually add an extra base case once I think I have enough, just to kind of give myself that little extra wiggle room. Mm-hmm. So you can never go wrong by having too many base cases. You can go wrong by having too few.
Yeah, and what Danny says is important if you think like, okay, well, if you have extra base cases, then you can have your induction or your recurrence kick in later, right? And that's fine. And we're not gonna check, right? Like if you have like I think it was 12 or 15 or 17 or whatever, you can start whatever you want. Okay. Just of course if you want to have more buffer, then you're going to have to do more work in order to figure out what those base cases are. And the higher you go, the more you're going to have to count with these things, right? You're going to have to think of more permutations. So,
luckily for
Yeah.
this, we just have to prove one exists.
yes.
So as you start getting higher in the base cases, then you kind of have a lot of the pieces that you need to build up one. But if we were asking for the total number of how many, then as you start to get more base cases, it's going to get more complicated to start to compute. Although if we were asking for the total number, you would need to do 7 base cases because you would need the reference of 7.
Yeah.
So here's that.
All right.
Anyway, sorry.
And then, yeah, that's fine. That's good points. Then we can, we have the inductive hypothesis now, that up to K, like this, there's always a way from 12 up to K to make, stamps for that many cents. Then we want to make, stamps for K plus 1 cents. So we want to find, we want to make sure that A sub K plus 1 is greater than 0. So we're gonna use the recurrence relation to get K plus 1 in terms of A sub K plus 1 minus 3, which I'll just write as K minus 2, and K plus 1 minus 7, so K minus 6. So we know A sub K plus 1 is this, and if our induction hypothesis is going to tell us that this A sub K minus 2 is going to be greater than 0, because we have this extra buffer of at least 2 back from this 14, that if K is at least 14, then K minus 2 is at least 12. So we know this A sub K minus 2. We know this is greater than 0. As I said, this is greater than or equal to 0 by the way we define the sequence. So we can say that this is greater. I can do it in multiple steps. We want the K minus 2. So we can just get rid of the A sub K minus 6. I'll say this is greater than or equal to A sub K minus 2, which is greater than 0. Yeah, because it has to be at least 12. And we've shown that we're our inductive hypothesis. Yeah, we've already covered the cases.
So I'll mention briefly, you could also do the same thing by like using the 7-cent stamps. You could say because you could add a couple more base cases and say because A sub K minus 6 is greater than 0, this always works. You could combine it and say since both are greater than 0, that this is actually going to be greater than 2. Greater than or equal to 2, I guess I should say. So you could put this together in different ways. The kind of shortest path is to just consider the 3-cent stamps here. But you can do it in more than one way. So if you included just the 7s or both the 3s and the 7s, then all of those will work as well.
Yeah. So before we go into are we done?
Are there do people have questions about this process?
Hey, why don't you do 14 minus 3? Why are you doing the K minus 2 that you got after the check?
Yeah, we've already shown explicitly up to 14. So we want to start at A sub K plus 1. We've already proved this is true for up to K equals 14. So the first thing that we need to make sure holds that this inductive case covers is that A sub 15 is greater than 0. So if we start at K equals 14, then because it's K minus 2 is K plus 1 minus 3, which I just wrote as K minus 2 to save space.
There's one thing I know some people are standing to go. So I have one like crucial, in my estimation, piece of advice, and this like helped me study throughout like my entire math degree and my CS degree. So you guys have a really nice advantage here in that you have a sort of idea of what the exam is going to look like, right? You know more or less the type of questions are going to be asked, and you even know more or less what the content of those questions is going to be. Of course, in the actual exam, the specifics will vary. So what I like to do when I study for situations like this, where I have a good idea of the kind of things that are going to be in the exam because of practice tests or whatever, I look at the practice test and I ask, okay, how could Sebastian change this in a way that is more or less the same difficulty, but like different? Because he doesn't want you to study this. Like, we're trying to explain everything. Yes. We don't want you to like study the test, right? We want you to study for the test. So let me give you a couple examples. What if instead of like calculating the GCD, you have to calculate the LCM, right? Do you know how to do that? What about, for example, in the next problem, we're going to have a recurrence relation and the solution is linear because the non-homogeneous term is constant. But what if it's not constant? What if it's a linear term? What if it has an exponent, etc.? So you should think about those things. Like, look at your problem as like a modular sort of thing. And it's like, okay, how can I modulate my problem? What can I change in this problem to make a variation of it that is similar in difficulty, that I can solve with the tools that I know, and that could possibly be in the exam?
You could even make it as simple as, what if I just change the numbers? So maybe for the wedding problem, I've still got 100 people, but now I want 10 bridesmaids and 2 maids of honor, right? Now you've got the same exact setup, but the answer is going to be different because the pieces of the problem are different.
Yep.
So you could kind of quiz yourself by doing just very simple changes like that.
Yeah. Another example. Okay, in that one, in the bridesmaid problem, it just so happened really nicely that we had like just enough seats for everyone. But what happens if I have excess seats, right? Then how do the problems change? Do they change at all? So these are questions that you should be asking yourself. That way, if they happen to appear in the exam, then we're not going to be kind of caught
unawares.
Yeah.
I was going to say caught unawares.
Oh, I was going to say with your pants down, but I don't know if that's an expression. So
it is, yeah.
Okay, it is. I was saying it would be kind of weird. Okay, we have one more exercise. Yeah.
So just like if we wrote this down on our exam, assuming it would be like the same question, would this be full credit for the problem?
Now it would be, because we explained it like this, and if you explain it just like this and we don't give you full credit, you can come complain.
I would say oftentimes when we put things on the board, we say things that I would include written in my proof.
Yeah.
So everything that's on the board plus a little bit of what we said while we were writing it is what I would look for full credit. So everything here, I would say would be like, if you just put what's up on the board, I would say would be probably an 8 out of 10 solution.
Yeah.
And I'd want you to include a little bit of some of the things we said. For example, like include a little bit of justification for how you came up with this. Include some reference to how you know these are positive. It's because of your inductive hypothesis, right? That sort of thing. So include a little bit of those pieces that we mentioned verbally, but this is like the majority of what you would need for a full credit answer on the exam.
Yeah, and this also, for me, you probably noticed I like to write very little on the board, right? I'm kind of allergic to writing manually. I only write with keyboards. So definitely when it comes to me, just like, again, parse what I said, parse the ideas of what I said, find your own way to write it down if you were to copy the same solution, but realistically the problems will be different. So, but yeah, hypothetically. Okay, so I guess
any other
questions about this?
We assume, or not assume, but like, is there a good chance that the question for recurrence relation will either be like the Discrete one or this line or the same?
I wouldn't like count on it. Those are pretty common like examples for recurrences because they kind of lend themselves to pretty simple recurrences pretty easily. Right. I don't have any other terms sitting around. I don't have coefficients. Right. It's not a super complicated equation. Right. So those kinds of questions, bit strings and stamps and these things lend themselves pretty easily to relatively like manageable expressions.
Unless you're
so I would say you will probably end up with something that gives you a pretty like manageable recurrence, but I wouldn't like count on necessarily seeing stamps or bit strings, right? There's other ways to have problems that will give you recurrences that look very similar to these and are pretty easy to work with.
Okay.
Want to be safe. Like if you write 7 base cases, you can use this and then you can reference these all, but.
Any other questions on this problem?
Because then you can reference back three from when it's a equals one. So if k is greater than or equal to 14, then we know we know a sub 12 is greater than 0. So we were looking at this. We're only looking at this and minus and we know this is if it depends on what you want to prove, but we wanted to prove this is just greater than 0. So we've already shown that this is greater than 0. So we can ignore this. Because once this is greater than 0, this whole thing is dead. That was the point.
Right, Julius, can we move on to the Alright, last exercise, guys, and then after that, we're gonna stick. Well, I'm gonna stick a little
I'll
bit.
stick around for a little bit.
Yeah.
I can probably stick around till 8 or so.
Yeah, probably
Answering questions, maybe a little longer if we've got a whole ton of questions, but yeah.
Okay, so for this one, it's another recurrence relation problem, and we're given that it's a sub n is equal to a sub n minus 1 plus 4 a sub n minus a sub n minus 2 or minus a sub n minus 3. I'm sorry, I'm kind of quiet, so if I need to get louder, just let me know. Plus 8. So part A is asking us to identify the homogeneous part of the, I guess, equation. So my knowledge on this is very limited, but to my understanding, it's just any part of it that involves a recurrence. So does anybody know what that would be for this one? Go ahead.
It's everything that doesn't include constant.
Yep, exactly. So I would put in
It's just a sub n minus 1 plus 4, and then apply all that except the 18.
perfect.
You could do this.
Does that make sense to everyone?
Yes.
Cool. And the next one is saying just prove that a sub n is equal to minus 24 as a solution to a non-homogeneous equation. Or non-homogeneous, yeah, right. So B is saying prove equals minus 24n. And when I first saw this, I was like, what is this kind of talking about? But essentially what you're doing is saying since a sub n is equal to minus 24n, you're simply just going to rewrite this as like anytime you see an n, you switch it to like for a sub n minus 1, it would be 24 n minus 1 and minus 2 for the other case and minus 3 for the last case. So it would look like simply just plugging that in essentially. So it's like minus 24 and minus 1 for that part. And then plus 4, 24 or minus 24, right? And minus 2. And then plus 24. 3 for that one, and then 18. So then it's simply just multiplying it out, which is tedious, but you'll get minus 24n plus 24, and then plus 4 times minus 24n plus 48 plus 24n minus 72 plus 18. No, 32. Okay, so you'll see cancel, cancel, and then this is minus 24 plus 18 minus 6. So then you'll get minus 24n plus 24. Did I mess this up? Yeah, no. Plus 4, that's minus 6. And then 24 minus 24, cancel, you'll get minus 24.
So
which is what we wanted.
I'll note real quick when we're doing this, we don't substitute in for this a sub n because our goal is to show that if it works on the previous ones, it comes out to what we want for a sub n. So it's much like how we would work in an inductive step, in an inductive proof, where I know it works for the prior ones, and I want to show that it works for this one. So I'm plugging in the minus 24n for the an minus 1, an minus 2, and an minus 3, but not for an, because I'm trying to show that if it put it in for those, it will come out to what I hope an becomes. So little tricky note there that could catch people unawares.
Yeah, so basically it's just some arithmetic. This one's not particularly challenging. Does it make sense to everyone?
Yeah.
I will say one thing about this, okay? Because the next problem doesn't, well, I guess depends on it partially, but notice here that your non homogeneous term will be 4 times 18, okay? This is, if I were to take this test, this is like the one thing that would be a perfect example of the thing that I think would change, right? I would expect this to be something slightly more complicated than a constant term, which would in turn give you a slightly more complicated particular solution. Now, in this example, you don't have to build the particular solution yourself. You don't have to in this example, right? Because Sebastian gives it to you and tells you, hey, this is a particular solution, check it, right? But you should really study how to build that yourself from here, how to build a candidate solution, and that's in the textbook. And for that, if you go there in the textbook, the notation is a mess, and like it gives me a headache looking at it. It's like theorem whatever. It's one of those. It's, I think it like one of the last boxes. But the textbook has some examples that are really, really useful on how to like look at the recurrence and find like a candidate particular solution depending on the form of your term. Yeah. Yeah, 8.1, 8.2, I think. 8.1, 8.2. Yeah.
And also, just as a general point, if you have trouble parsing through the like really symbol heavy, non-explanatory things in the textbook, that's the kind of thing we can help you with too. Because as Mario said, like even when we know what's going on, sometimes it's hard to figure out what exactly the textbook is trying to say, and it's sort of like condensed form. So we don't always expect you to be able to parse through exactly what is going on there, and we can really help you do that. And that can be sometimes a helpful way to help prepare for these exams, because we can kind of pull back the curtains a little bit, what's going on behind the scenes for some of these things you'll probably need.
Yes, that said, and maybe not necessarily for the midterm, because reading the textbook takes time. I know reading textbooks takes time. I know some of you do not read the textbook at all, and I do urge you for the final at least, but maybe for the midterm to read the textbook. And there's something I like to do when I want to read through the textbook and want to see what's in it and get an idea for what's in it and the sort of things it discusses and examples, but I don't want to read the whole thing. So something that you can do is go through the chapters that you're struggling with and then look at all the blue boxes. The blue boxes have definitions and theorems. So it's usually like the meat of the chapter will be in the blue boxes. And then if there's a blue box that you don't get right away, what you can do is usually right after there's going to be an example of two. And then you can see, okay, how does the example relate to the blue box? And this is something I say in my sections all the time. Understanding an example of a concept is not the same as understanding a concept, okay? So make sure that when you read the example, you don't just go like, oh yeah, that makes sense and move on. Like make sure you actually understand it. Because I've been victim of this all the time, right? My brain plays a trick on me and makes me think that I actually understood. But it's very much like when you're reading a book and then you like snap out of a trance and you realize that you read 3 pages, but you didn't retain any of it because you didn't pay attention. The same thing can happen at a micro level with examples. So when you read the examples, read them carefully and try to see how the example relates to the definition. So you don't have to read the whole chapter. You don't have to read every chapter, but definitely for the parts that you're struggling with, I would suggest read the examples in the textbook, because the examples are pretty well laid out and they do not really use that mathematical mumbo jumbo that sometimes gives us headaches.
The other thing I'll say, if you come across a definition or a theorem that confuses you, in addition to examples or proofs of it that come afterwards, the prior paragraph will usually give you a bit of motivation as to why do we want this? Where does this come from? So that can also be helpful with parsing through what the definition means, because usually it will come across as something like, well, we'd love to be able to play with this kind of a thing, but we don't have the tools we need. So we're going to put together something that kind of behaves in such and such a way. And then they'll give you the definition of the thing that we're putting together to do that. So those sorts of things can be helpful tricks to kind of parse through what's going on in those.
Okay. Sorry.
No, sorry. I'm not C.
Oh, you're done?
Yeah.
Oh, okay. Well, I already struggled with the algebra at the beginning, so hopefully I won't struggle again. Problem 3 is part C is unless you want to do it.
Go for it.
Okay. Oh, yikes. Okay. So problem 3 is part C is really just solving a system of equations. Like once you get down to it, once you plug in the things and you understand what to do, it really is just solving a 3x3 system.
So I will say right now, going through the linear algebra of solving those 3 things is probably not really worth our time right now. Getting to that point and figuring out how to find the roots and whatnot for this problem is, I think, more worth our time to figure out the setup. So I would expect we probably won't actually solve through for those 3 variables, but showing you how to look for them is the more helpful portion of it.
Yes. And this is, again, just following essentially an algorithm or doing like sort of template matching, looking at your blue box in the textbook, which I'm sure you're kind of going to write down in your A4 page for the exam, and then be like, okay, what goes where? How do I plug these things in, right? So the form of one of the solutions of these things typically looks like this. So you have the let's just do like, I guess, R. So you're gonna have some coefficient, and this can be alpha, but I don't know why. I guess sometimes like writing Greek letters gives the problems a sort of mystique and makes them appear more complicated than they are. I don't know if I'm the only one.
I actually like Greek letters.
I love them.
Because sometimes you can use Greek letters and Latin alphabet letters to denote things that behave slightly differently. For example, something I'm looking for a solution for versus a constant that I don't care about the solution for. So it's a useful thing to have in your kind of toolkit, the ability to write some Greek letters.
Yes, definitely. And it makes your math look like more esoteric. So then when someone like glances over what you're doing, it looks like you're really smart. Like, don't tell me you hadn't thought of that before. Okay, and then in this here, I'm gonna have I guess the particular solution. So I'm writing this in very generic terms. So once you find the solution to the homogeneous part, and then you find a particular solution for the non-homogeneous part, the final thing will be a sum of both solutions. So you have this part is like the solution to like what this would be, what the solution would be if it was just a homogeneous linear recurrence or whatever. And then this part is what we add afterwards. So what are the R's? This should be R1, R2, R3. These are going to be our roots. They're going to be the roots of the characteristic polynomial. So hopefully by now, you guys know how to form that characteristic polynomial. In this case, the characteristic polynomial has to form 1 minus 1 4x plus 4. So you have this characteristic polynomial here. Yeah. And then you have to find the roots of this thing. So we've gotten like tons of questions about like, well, I don't want to find the roots of this thing. It's like a cubic. There's many ways of doing that. I just replied to the Slack to someone of like a couple ways of doing that. But like realistically in the exam, we're probably going to give you a hint. It might not be
if it's not a quadratic or linear, you will probably be given a hint on how to do it.
Yes.
So we will expect you to be able to factor and find roots of degree 2 or lower. I do not expect you to be able to quickly find the roots of anything that's degree 3 or higher, even though there is a formula for degree 3. So there will almost certainly be helpful advice if the degree is 3 or higher.
Yes. So the hint in this case we're talking about is a factorization. So that factorization is x plus 2, x minus 2. So if you need some review from this, we can look at the roots because we look at these different terms and we see that, well, if I plug in 1, right, this is going to be 0. So it's going to 0 out the whole thing. If I plug in minus 2, negative 2, it's going to 0 out the whole thing. By the way, if I say minus 2, it's just like a Spanish thing that I like never kicked out because we say menos dos, which would be like -2, but it's negative anyway. And then here it will be 2. So those are like the different things.
If you want a real throwback to algebra, the zero product property is what allows us to split up all 3 of those roots. Real throwback to high school or middle school algebra courses there.
Yeah. Okay, so once I have my roots, I just go back to my form here, and I'm going to plug them in. And I'm going to say, okay, well, that's going to be 1. That's going to be -2. And this is going to be 2. The nice thing is that the 1 to the n is just going to be 1. So this is going to become constant in alpha. And once I have this, I go back and I say, okay, what is my my specific thing here? Well, we saw it was -24n, right? So we're going to put the 24n in there, okay? And now you can think of this as like, like a relation. You can also think of it like a sort of like sequence if you're more comfortable, as a function. And you can say like this. And why do I say if that makes you more comfortable? Because essentially, once we have this, what we're going to have to do is to use this data to find out what these values are. So if you look at this, right, and I plug in the n, this is the n, right? If I plug in the n here and the n here, then this is going to be just a number, and this is going to be just a number, right? So let me give an example. If I go,
Yeah, 24n, which is 24.
oh yeah, 24n. If I go A0, this will be alpha plus, well, -2 to the 0 is just 1, so beta plus 1. Then the same here, -24 to the 0, that's 0. So this is my first equation, right? And then we do the same for the second one. I know I'm kind of too low maybe for some of the people at the back. Well, kind of have committed to it. I'm sorry, guys. And then we do the same for 1, and this would be alpha still. So you're going to have alpha in all of them, which hint means you can probably just ignore that. And then save it for later. And then here, -2. So -2, this would be -2 beta plus 2 gamma minus 24. And then the last one, A2, would be alpha again, minus plus 4 beta plus 4 again, 4 gamma minus, and this would be 48. And there you go. Once you have this, you should know how to solve this from like linear algebra, right?
We've got 3 equations and 3 unknowns.
Yes.
That's all we need.
Yeah.
And we can solve that now.
And just to be specific, this would be 1200. Yeah. So just because we have like our esoteric Greek letters doesn't change the fact that it's just a linear system. This is x1, this is x, this is y, this is c, or whatever, right? And then you just solve that. And that takes some work, right? So you should probably practice how to solve a 3x3 system or 2x2 system, or just practice to make sure you know about that.
Yeah, so I would expect all of you would be able to solve a two unknown system. It becomes more complicated with 3, but it is exactly the same principle. I like to do these with substitution. That's my favorite tool for these. You can do these with other tools as well. You can use matrices if you know how to do that. Different things. But yeah, it doesn't actually come out to being excessively complicated. It's just time consuming at this point.
Mm-hmm. Yeah, so just keep in mind all the components of this, right? We have, again, just to kind of wrap it all up, we have the homogeneous part, which gives us this part of the equation. We already plugged in the roots that we got from the characteristic polynomial. Then at the end, we add a particular solution. And once we have this expression, an, all we need to do is, given some initial conditions, we instantiate the values of these things, of these coefficients, and then it becomes a system that's linear in alpha, beta, and gamma. And that's it. You do some beep boop on your calculator and you get the answer. And then a nice thing about this is you can check. You can check on your calculator, you can check. So anything that has you like solve an equation, you can check, and you should check, because like you might make a mistake and you might go, okay, whatever, and not check it. And that's my philosophy. I always check on myself. Yes, it is not the only answer.
Like, I don't understand.
So I think particular there refers to like this particular option for a solution, and not like.
Would they do today's
So like it refers to like this is one solution. Check this one. It's not saying it's the only solution. So I think that's what particular is trying to convey there.
Yeah.
Is that your understanding too?
Yep. Mm-hmm. That's right. I would prepare, because I can't. I would love to tell you no, but I don't know.
Yeah, we aren't involved in putting this together. That's all Sebastian.
Yeah.
So it's our best guesses as to what's going to be, but we can't say for sure.
Okay, so we are done. Thank you so much for coming, making time to come. Hopefully it was helpful.
We'll or some of us at least will stick around for a little bit if you have other questions. You think there's a meeting to be all day? Thank you so much. This. Mario, did you record this? And if so, will you be posting it?
Yes, I did record.
Yes,